All right, related rates 3, hopefully our last related rates for a little bit until you get really good and we need to review near the end of the year. All right, a child is playing with a small spherical balloon, a point 150 feet from his mother, both of which, the mother and the child, are on level ground. So let's get a picture of that before we do anything else. All right. So here's the kid. He's got a balloon, and his mother is over here. Oh, that's not right. And his mother is playing with her cell phone because they're at the park. Okay, cool. That's 150 feet away. That's not changing. Okay. The rate at which the tears come from the child's eyes is 1/2 centimeter cubed per minute, which of course doesn't have anything to do with the problem, but children do cry a lot. The balloon rises straight up 8 feet per second. Oh, I get why he's crying. So this distance above the boy, I'm going to call h, which means that's dh dt, 8 feet per second. And since h is growing, that's a positive 8 feet per second. How quickly is the balloon moving away from the mother when the balloon is 50 feet in the air? Right. So I need to know this distance. I'll call it z, between the mother and the balloon, which means I'm looking for dz dt. And I guess 50 feet in the air, we're going to do h is equal to 50 at the end once we're there. I can't put in that 50 because unlike the 150, the 50 is not always true. Okay, so let's look at this picture. That's a right triangle, and h squared plus 150 squared is equal to the hypotenuse length squared, taking derivative with respect to time, 2h dh dt, plus 0 is equal to 2z dz dt. I'm going to divide out the 2's. Maybe I'll just cross them out. And h is equal to 50. dh dt, that's the 8 we already found. Z, oh man, what is z? Z is, when the balloon is 50 feet above the boy, what's the distance between the mom and the balloon? And that is, Pythagorean theorem stuff, the square root of 50 squared plus 150 squared. It's best to do that, you can grab a calculator if you want, but if you're going to use a calculator on a problem like this, the thing you should do is wait until the end to use your calculator. So I'm going to have 8 times 50. I'm not even going to multiply that out, even though I know it's 400. Because if I'm using a calculator, I'll just do everything all at once and write, dz dt is equal to whatever the heck that is. My guess is you don't need my help writing out the conclusion, so I'll say it. I'm not going to spend the time writing it. When the balloon is 50 feet in the air, the rate at which the balloon is moving away from the mother is, whatever this number is, 8 times 50 over the square root of 50 squared plus 150 squared feet per minute. No, feet per second. Okay. So I want to get to this. So this child mentioned earlier is now flying a kite, but is still crying and it's about to get worse. I think his kite is going to go away from him. Okay, so he's flying a kite. And that would be a solid kite. It's all in the details. Okay, so there's my kite. The kite is 90 feet above the child's hand. Oh, this doesn't make that much sense. Let's go slowly. The kite is 90 feet above the child's hand level, and the wind is blowing the kite horizontally 5 feet per second. Okay, so the kite is moving 5 feet per second horizontally, which means the 90 is the height of the kite above the child. So that's one leg of a right triangle. So I guess this horizontal distance is changing. I'll call that x, which means this 5 is dx dt. And that's going to be positive because that length I've labeled x is growing. How fast is the child letting out the kite string when 150 feet of string is out? I'm going to call this diagonal length z. And we're asked for dz dt, how quickly the kite string length is changing. And z is going to be equal to 150. Not always, but just at the moment in time in question. So another Pythagorean theorem one, and we're going to have x squared plus 90 squared is equal to z squared, 2x dx dt is equal to 2z dz dt. And just like the last time, we're going to divide out the 2's. Let's see, x is a Pythagorean theorem thing. So I'll put in dx dt first, 5. Z, that's 150. dz dt is what we're looking for. And x is going to be the square root of 150 squared minus 90 squared. So that means dz dt, the rate at which the string is being let out, is 5 times the square root of 150 squared minus 90 squared, all over 150. Okay, I think we're making progress here. Maybe I should make this slightly wider. Okay, the child's balloon is so high and expanded that it has sprung a leak. The air escapes at a rate of 2 cubic feet per minute. How fast is the surface area shrinking when the radius is 12 feet? Yeah, that's a really big balloon. Okay, so we have a big spherical balloon. I like to draw dashes on my spheres. And maybe it didn't spring a leak there, but air is coming out. And the rate at which air is coming out, well, is 2 cubic feet per minute. So that's a change in volume. So dV dt is minus 2 feet cubed each minute. How fast is the surface area shrinking? Surface area is S, so ds dt is the thing we're looking for. Now that seems a little bit difficult, and this is the reason I'm making a video, because this problem is a little bit confusing, but once you see it, it's kind of elegant, straightforward, whatever you want. So volume of a sphere is 4/3 pi r cubed, and the surface area of a sphere is actually just the derivative of volume, 4 pi r squared. And we know we need both of these because we need dV dt, which is the derivative of the equation on the left, and ds dt, the derivative of the equation on the right. So maybe I'll find those. The derivative of 4/3 pi r cubed is 4 pi r squared, dr dt. And ds dt is equal to 8 pi r, dr dt. And so we want ds dt right here, which means we need an r, which we have. That's going to be 12. It says when the radius is 12 feet. But I guess we need dr dt, which seems impossible. But the other equation has a dr dt, and we know the radius 12, and we know dV dt. So that's our plan. We'll fill in dV dt as -2, and we're going to do 4 pi times 12 squared is dr dt. And then, maybe I'll rearrange. Okay, so dr dt is equal to -2 over 4 pi times 12 squared. So then I'll put that into ds dt over here. And we get 8 pi. Instead of r, we write 12. And instead of dr dt, we write this thing that we just figured out, -2 over 4 pi times 12 squared. So we're actually kind of done. The pi's divide out. One of the 12's divide out. So that's -16 over 4 pi times 12. Nope, not 4 pi times 12. Negative 16 over 4 times 12. And ds dt, what is that? Well, that's just negative 1/3, and that's feet squared. Is it per minute, per second? Per minute. Hopefully you can figure out the rest of it from there. So, poor kid, he's going to find a fourth thing to do. The child finally gives up and decides to play in the sand. He takes a bucket of sand to the top of the play structure and dumps it off. Hold on, I can do a bucket. Let's see, a sand bucket looks like that. It always has kind of a hoop on it, and this sand is falling out. Strangely, the height of the pile is always equal to 4/3 the radius of the base. If you've never dumped sand into a pile, it basically is shaped like a cone. So let's see, the height of the pile is always equal to 4/3 the radius of the base. How fast is the volume changing? So we want dV dt. When the radius of the base is 3 feet, so radius is 3, and the radius is increasing, dr dt, at 3 inches per minute. Now the thing is, hopefully you noticed, dr dt is no good. The rate of change of the radius is 1/4 foot per minute. We need to make sure that we have all our units matching. Volume of a cone is 1/3 pi r squared h. And in this case, we don't want the h. And, we were already told that 4/3 r is always equal to the height. So the volume we can rearrange to be 4 pi ninths and r cubed. So that's a much easier derivative. dV dt is equal to 4 pi thirds r squared dr dt. And dV dt, it's time for me to pick up one of my daughters. I don't know if you can hear my watch going off. 4 pi thirds, the radius is 3 feet at the moment in question, and dr dt is 1/4. So dV dt is equal to, one of the 3's divides out, the 4 divides out, and that's 3 pi feet cubed. He's dumping a ton of sand. Feet per minute, feet cubed per minute. Is that right? That seems like a really big number. 1/4. Seems right to me. Have a good day.